I'm Mark Cavanaugh for Cavi Coaches, and today we're going to conduct a lab investigation, and I'm going to coach you up on the difference between mass and weight. Alright, so what I have set up here is I've got a ring stand and I've got a spring scale. Spring scale, same thing you'd find in a grocery store if you wanted to figure out how many pounds of apples that you needed. So mine's just not calibrated in pounds, it's calibrated in newtons. And I've got a hanging weight, and I put the whiteboard up here so you have a better background so that you can see it. So the first thing we're going to do is we're going to go ahead and draw a free body diagram. So pause the video and draw a free body diagram for this. Had the tension force of the spring scale pulling up equal to the force of gravity pulling down on the mass. So now what we're going to do is we're going to talk about things that we can change and measure. Go ahead and make some observations. Think about some things we can change and measure. Go ahead. All right, so you saw some of the things that my students would change. So what we're going to do is we said that we could change the mass of the hanger. So mass is measured in kilograms. Mass is a measure of how much matter that an object has. Weight, now weight is different. Weight is the amount of gravitational pull on that mass. So what we're going to do is we are going to conduct a lab investigation. Our control is we're going to stay on planet Earth because I don't think any principal would be able to approve a SpaceX field trip so that we could go to the moon to conduct this experiment. So we're going to stay here on Earth. That's going to be our control. So what we're going to do was the fact that it's stationary, we could have moved it, accelerated it up or down. And we're going to leave that at control as well because we don't want our free body diagram to change. So we had the tension force of the spring scale pulling up equal to the force of gravity pulling down on the mass. And we want that free body diagram to stay the same. So we're not going to change the motion. We're going to keep it at a constant zero velocity. So what we're going to do is we're going to change the mass of our hanger, and we're going to measure using a spring scale calibrated in newtons to measure our force. So now you've collected your data, and now you want to analyze that data. So how are we going to analyze that data? Well, first we're going to create a graph, and we're going to plot the weight or the force of gravity on the vertical axis, and we're going to graph mass, make sure you convert it to kilograms, on the horizontal axis. So we're going to plot all of our points for the different masses and the weights that we got. And we find that we get a pretty linear function. So we're going to go to our graphical method summary sheet and we're going to figure out the mathematical equation that we're going to use, this simple y equals mx plus b, the simple version of slope-intercept form. Now we're going to substitute in for each of those variables. We're going to substitute force of gravity in for y. For the slope, remember I like to put the slope in parentheses, so we open parentheses. This way the units are separated. So let's say we got a slope of 10. And we look at our units on our slope. What are our units? Well, the rise is newtons and the run is kilograms. So that gives us a unit of newtons per kilogram. The closing parentheses separates the units from the variable, the x variable, and we can see on the horizontal axis we graphed mass. Now we look at our vertical intercept and we can see that the vertical intercept is 0. Well, what does that mean? Well, if there's no mass hanging on the spring scale, it should read 0. So the slope is the connection between mass and weight. The actual value of the acceleration due to gravity is 9.8 newtons per kilogram, or 9.8 meters per second squared. So what does the slope mean? 9.8 newtons for every kilogram, 9.8 newtons of force for every kilogram of mass. So that means that the Earth supplies 9.8 newtons of force for every kilogram of mass. This number is called the gravitational field strength constant, or the acceleration due to gravity. And this value is so important on Earth that it gets its own symbol. And that symbol is lowercase g. Our general equation is the gravitational force is equal to, and the general way to write this is the mass comes first. So you write mass times lowercase g. Don't write capital G because capital G is a completely different constant. So we have our equation that the weight of an object, or the gravitational force, is equal to mass times g, g representing 9.8. So now we have a way to quantify the gravitational force. Congratulations. Have a great day and an even better tomorrow.
If you found this video helpful, don't forget to subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.